Hi. In this lesson we're going to look at forces involved when an object is placed on a slope. And there's one specific learning intention that is covered in this, in H there. So resolution of the weight of an object on a slope into component forces parallel and normal to the surface of the slope. So what we have is, let me just draw this for you. We've got a slope, and this slope will make an angle of theta to the horizontal. The object will have a mass of m. And now we're going to analyse the forces on what's happening here. We don't need to worry too much at this point about whether the slope, the object is moving down the slope or if it's stationary. If there's a friction-free slope, it's just going to accelerate down the slope. If there is friction, enough friction, then it will stay stationary. But let's just look at what the two forces acting on this are, if we forget about any friction on the slope just for now. So, well, the only force really that is acting on this is going to be the force of weight, or the force of gravity, I guess. So let's just get W. So the weight of the mass is going to be acting vertically downwards. Now, this weight is going to be split up into two components. And if you remember, a couple of videos ago, we were looking at splitting up a force into its horizontal and vertical components. It's similar to this, but it's not quite the same. You would be mistaken to think that theta and then the weight is opposite the theta. Just pay very close attention to how this is worked out. Now, this weight is the only force acting on the object, but that force is split up into two different component parts. And that first component part is going to be a normal reaction force. So your normal reaction force is going to act at right angles there. Well, this is the force that the slope would apply in the mass, and the mass would be having an equal and opposite force on the slope, like so. It's also going to have a component of force acting down the slope. This is generally what we're interested in. So we're interested in the downslope component of this force. Now, we have vectors. This is going to be our hypotenuse. This is the biggest force here. And then these, the blue one and the green one, are components of this weight. So if we add these vectors nose to tail, let's take the green and just put it down here. So what I can do, I'm going to make my triangle a little bit bigger. There. Try and get the same angle. And then just extend this off. So this is the normal reaction force. This is the force down slope, and we have our weight. Now, if we look at the angles of this, what we have is we have this triangle here and then this triangle here are identical. Now, if you don't believe me, then well, let's just do a little bit of geometry here. This is going to be a right angle in here. This is theta, and so this must be 90 minus theta. Okay, because the normal reaction force, so this is 90 here, this triangle must be theta as well. Because if that's 90 minus theta, then this is the z angle in here, so that's going to be the same. 90 minus theta. So we've got a right angle triangle here. We've got the z angle there, because this and this is parallel, and so we know that this is theta here. Then we just use SOHCAHTOA to find out our different components of weight. So first of all, force down slope. So force down slope, it's the green one we're looking for, and so we've got theta up here, opposite its sine. Sine theta is opposite, so we've got force down slope over weight. Rearrange for force down slope. Is equal to W sine theta. Expand that out because W is mg, so we'll have force down slope is mg sine theta. And then we'll have the normal of weight. So the normal component of weight, that's going to be adjacent, so this is going to be cos theta. Again, rearrange. So force normal is equal to W cos theta, which is going to be mg cos theta. So there's your two components for an object that's on a slope. Now, in almost every case, I don't think I've ever recall seeing a question that has asked you actually to use this, but well, let's just think about this for a second, that cos theta times the weight of the object, in almost all applications of this, I guess, where we're looking at an object on a slope, the normal reaction force is going to be the force that's provided by the slope is going to be equal and opposite to this normal reaction force. And so in almost every circumstance, the force is going to be balanced, and therefore we can generally ignore it. But what is not the case is that this force down slope is mg sine theta. Now there's a number of things that can happen. So, well, I guess if I draw some, so example 1, and I just have an object on a slope. So I'm going to have here mg sine theta. Now if there's no friction, then the entire force Fun is going to equal force down slope, which will equal mg sine theta. So in the example where there's no friction, the acceleration of the object is just going to be its mass times this. Example 2. We can have an object, again, like weight, mg sine theta won't change. But what we can have is we can have friction. So let's just say small friction. So we'll have a small friction there. And in this case, Fun is going to be force down slope minus friction, which is then going to provide the unbalanced force. And so we subtract these two force vectors, they're in the same plane, We subtract them, and then from that we can get MA and the acceleration of the object. Finally, we could have an example where there's a large friction. So friction, force down slope, and at this point, if the friction is large enough, then fun is going to be 0. There's going to be no unbalanced force because force down slope is equal to friction. In this case, the object is not going to be moving at all. It'll just sit stationary on the slope. Obviously, increasing the angle is going to increase mg sine theta, and if the angle increases so that mg sine theta becomes larger than friction, then it can start sliding down the slope. Now, this formula here is not in your formula sheet. Although it's an individualized formula, it's not in your formula sheet. And I think it's probably going to be a bit of a stretch for you to kind of derive this ad hoc with a given question. The recommendation I would have is that you should try and learn this formula as it is. If you see a question involving something on a slope, a truck, a marble, a person in a little dinghy sliding down a water slide, anything. If you see an object that's on a slope, invariably you will have mg sine theta, and it's a really, really good formula to remember. You don't have to remember many formulas in physics because you've got your formula sheet, but this is not on there, and you 100% should remember this formula. It will save you trying to go through this, which is pretty tricky. Right, let's look at a few worked examples of this. For this example, we can have a slope, 40-degree slope with a mass of 5 kg placed on it. We're going to say calculate the acceleration of the 5 kg mass, assume that the slope is frictionless. So we'll start off with our formula. So force down slope is going to equal mg sine theta. Make the substitution. 5 kilograms times 9.8 times sine 40. That'll give us 31.4 something, so let's just call that 31 newtons. Okay, we can go on from there now. Example 2. Oh, sorry, I'm not finished. Now we calculate acceleration. So now we're going to calculate acceleration. So unbalanced force is MA. Now, if there's zero friction, then at this point you're going to have 31 newtons as the unbalanced force. Therefore, acceleration is fun over mass. 31 over 5. 6.2 meters per second squared. So now what would happen if there was friction? So here we have an example above. Calculate the acceleration of the mass if the friction on the slope is 20 newtons. We would go through in exactly the same process of working out force down slope. However, At this point, the fun is not going to be forced down slope as it was before. So here, our fun is going to be force down slope minus friction. This is then going to be 31 newtons minus our friction, which is 20. That's going to give us an unbalanced force of 11 newtons. And from this point on, then we can just do exactly the same. A is fun over m, which is 11 over 5. Which is 2.2. So 2.2 meters per second square. So in example 3, we'll build this up slowly. We'll do quite a bit with this example just to demonstrate what can be done. But to start off with, nice and easy, we've got a mass on a slope. It's a 30-degree slope. The mass is going to slide down the slope. We're going to have friction of, let's just say 10 newtons. No, let's actually just say friction. Yeah, friction. It's 50 newtons. Okay. So box is going to slide down the slope, presuming that the downslope component of force is greater than the friction. It's going to slide down. As it gets to the bottom, we have this special spring-loaded launcher that is going to come and it's going to hit the spring, and we're going to assume that it's an ideal spring launcher. No energy is going to be lost, and whatever velocity that it hits the spring with, it's going to be returned back up the slope at exactly the same velocity. So no energy is going to be lost, but we'll come to that later. We'll do the first two bits first. So draw a free body diagram showing the forces parallel to the slope at the start. Free body diagram. Simple. Try and get them roughly parallel. So here we're going to have, if the box is going to slide down this way, then we're going to have friction acting up that way. So friction and there. Now it's saying force is parallel to the slope, so we don't need to worry about weight or the reaction force. So we'll just say force down slope. Okay, done. So that's A. B, as before, in exactly the same way. First of all, calculate force down slope. So we'll have 19.6 newtons. Then work out unbalanced force. So fun, force down slope minus friction. We'll have 19.6 minus 15, which is going to leave me with 4.6 newtons. And my acceleration A is equal to 1 over mass which is 1.15. So part C, I've now said that the slope is 3 meters long. We've worked out an acceleration, and the question is asking us to calculate the velocity of the mass at the instant it hits the spring. So it's going to start at rest, it's going to accelerate all the way down at 1.15 meters per second squared for those 3 meters until it hits the spring. And we're going to calculate the velocity of that. So, part C, we're going to look for a velocity. We have a displacement, we've got an acceleration here, and so we're going to use equations of motion to find this. So equations of motion will have suvat, and fill in what we know, what we don't know. We don't need time. Acceleration we've just worked out to be 1.15. V, that's what we're looking for. We've got a displacement of 3 meters, and our initial velocity was 0 meters per second squared. So we don't need t, we've got s, u, v, and a. The equation of motion, third equation of motion, v squared equals u squared plus 2as. And that's just going to be 0 plus 2 times 1.15 times 3 and so V is then going to equal, well, I'll just do all this all in one. We see 2.6, so let's see if we say 2.63. So it'll be travelling at 2.63 meters per second by the time it gets to this point. Now I'd said that it's a perfect spring. It's going to release the mass back up the slope at exactly the same velocity. So we're going to have this now moving up at 2.63. Part D, draw a free body diagram as it moves up the slope this time. So D, same object. Now at this point, this is a really good teaching point, and it's quite often asked. So at this point we have the velocity is in that direction. So the velocity is moving in that direction, and the first time that our velocity is coming this way. Now friction always acts against the motion of the object, so if the object is coming this way, then friction is going to act against it. In this case, friction acts against the motion of the object, and because it's moving back up, then our friction is going to act in this direction here. So we're going to have our friction there, and of course downslope component of force is now going to act in this direction as well. Okay. And the last thing that we're going to do, part E, should have planned this better probably, but how far up the slope will the mass travel? So what we can have, let's just get a bit of more space here. So part E. Let's think about what's going to happen. So we're going to have now the two force vectors are acting in the same direction. So what we're going to have is rather than right back at the start when we calculated the force down slope, that's going to still be the same because the mass hasn't changed, the angle of the slope hasn't changed, indeed the friction hasn't changed, the friction is still going to be 15. But the crucial thing here is that our unbalanced force is not going to be 4.6 newtons anymore. Our unbalanced force is going to be force down slope plus friction. And so we're going to have 19.6 plus 15 34.6 newtons. Our acceleration so 34.6 divided by 4, 8.65. Now, the object here is moving up the slope, so here we can say that the velocity is going in that direction, and we calculated that the velocity hit this spring at 2.63, and if it's an ideal spring, the velocity at this point is going to be 2.63. Now what I'm going to do is I'm going to assume that this direction here, so I'm going to say that this is going to be positive. And this is important. Before, we haven't really talked about vector sense of things. Everything was going down, everything was positive, it's fine. But now we have opposing vectors. We have an acceleration vector which is heading down the slope, and we have a velocity vector which is going up the slope, and so they're going to differ in sign. And so I'm going to just say, I'm going to make a statement that upwards is positive, so everything from this point going that way is positive. It means my displacement that I calculate, and I am hoping that you're figuring this out, that it won't return to its starting position because the acceleration is much greater. So the finish point is going to be from there, so we're going to have a positive displacement, we've got a positive velocity, we've got a negative acceleration. And so here, just so we don't forget. And again, Suvat, exactly the same formula, but we'll have slightly different quantities. So Suvat, again, don't care about time, acceleration minus 8.65. My velocity, so my velocity, well, my velocity is not going to be this, my velocity, which is the final speed, final velocity there, and my initial velocity in this case is going to be 2.6 meters per second, and I'm looking for S. So I can have v squared equals u squared plus 2as, 0 is equal to 2.63 squared plus 2 times minus 8.65 times s. Oh, sorry, I'm squishing this up. It's not great. So let's just take it down here. Rearrange this. I'm going to have S is equal to 2.63 squared over 2 times 8.65. Leave this where it is, take all of this over to the other side, divide then by that, and we'll get this expression here, which will give us 0.3998, so let's call it 0.40, so 40 centimeters. So travelling back up the slope, the object will only move 0.4 meters up. The takeaway from this is that, and the point of this example is to highlight the importance of your free body diagrams. As it's moving down the slope, the velocity vector is coming down with the downslope component of force, so friction acts against it. Whereas as it's moving back up the slope, both force vectors are in opposition to the velocity vector, and so the acceleration, or the deceleration as it would be, is going to be much, much greater. Right, so that is downslope component of force or downslope component of weight. There's plenty of problems which you can practice, but thanks for watching. Bye.